Hello, welcome to the pedestrian activity practice exam. This was PA from December 8th of 2020. To start, you will already have read the project statement. You would have 15 minutes during your waiting period when you're filling out the survey, in which case you can read through this. Then you'll have two files, the solution, the template file in R and the template file in Word. So the first thing that I do is move these to separate windows. And in RStudio, I go up to Appearance and zoom out here. Set it to about 80%. Okay, and then we have the project statement. So I'll skip over this general information for candidates because you will already have read through this several times. The business problem. Your actuarial consulting firm has been hired by a national retail firm to help them understand the factors that affect pedestrian activity. They have noted that their sales are proportional to pedestrian activity near their existing stores. When considering new locations across the U.S. for stores, insight into how weather affects pedestrian activity would be useful. For existing stores, it would be useful to understand how pedestrian activity varies by time of day, day of the week, and when deciding what hours to be open. The data for this study consists of hourly counts of pedestrians that were collected in 2017 and 2019. The exam data is derived from a public data set by the New York City Open Data. So first of all, the thing that I notice is that it says insight into how these factors affect the weather. So they're just looking at inference. They're not looking at predictive power. Some cleaning was performed in advance. The data dictionary at the end of this document describes the available variables. It's not necessary for you to paste the dictionary into your report. I noticed that there are only 1, 2, 3, 4, 5, 6, 7 variables. So this is a low-dimensional data set, mixture of factor and numeric. The tasks are intended to be done in order with results from one task informing work in later tasks. Graders will look at the solution for a given task within that task's area of the RMD file. In all cases, you should justify the choices that you make in your report. Okay, 7 points, explore the variables. So it's about 5 points is about 15 minutes. So this question should take about 15 to 20 minutes. Your assistant has supplied code that allows you to consider each variable alone and in relation to pedestrians. So hypothesize which variables are least likely to have significant contribution to your model, and hypothesize which variables are most likely. Okay, so first of all, I can just notice, whoops. So these histograms are not informative of which will be predictive of pedestrians, apart from showing the spread of values. You know, variables, if a variable had, all values that had many zeros or missing values, then we would, be able to see this from the histogram. In this case, we do not make any conclusions. The next graph is these count values. So I just say this graph shows the counts and not pedestrians. Notice that weather has only a few values for rain, sleet, snow, wind, and fog. So these records, these factors, levels are of questionable credibility. There are the same number of records on all days of the week. Next graph, weekday. So you notice that this trend is basically flat. Whoops. Right along here. The green line, whoops, let's go below. Box plots, weekday, shows that the median, about 800 pedestrians for all days of the week, except for Saturday. Saturday have about 1,000. This implies that weekday is not predictive. However, we need to consider interaction terms with other variables before being able to make this conclusion. Next variable, weather is not reliable because there are many factor levels which have only a few records. There is also no clear distinction between what the levels represent from a business. Like, what does a clear day look like? How does that compare to partly cloudy? These are questions which, will make, these are questions which do not have a definite answer. We can look in the data dictionary and see, okay, this is the hourly condition, weekday temp forecast. So it just says hourly weather condition, but does not specify, how this is measured. Are all measurements? Yeah. So in other words, the data is questionable. Next one. Okay, this is the hour variable. So I noticed that there's this trend where it starts out low and then has a peak in the middle of the day and then goes down, where most pedestrians go out during the middle of the day from 10 a.m. through, what are these values? Hour is the beginning of measuring hour, integer from 6 to 22. So this is 6 a.m. and 22 is 10 p.m. So the middle of the day, so 10 a.m. through 5 p.m. And I would just say the time is measured by hour, which records the number of pedestrians from 6 a.m. through 10 p.m. So if you look at the minimum and the maximum values, so during the early morning and night, there are 0 pedestrians, whereas during the day, there are between 1,000 and 2,000. This implies that hour is strongly predictive of pedestrians. The next variable, temperature. So the temperature graph is difficult to interpret. The graph is not well specified. A dot choice of a dot plot here is poor because there are many points which lie on top of one another. The trend line shown in blue, does help by showing the average pedestrians. However, a different type of graph would be better. So in your exam, this is the exact cheat sheet that you're going to have. You go to Help, Cheat Sheets, Data Visualization with ggplot2. And in our version, we have removed the information that you don't need. So in that case, you won't even need to look at it. But so I'm going to look at the data visualization cheat sheet. And here I see geom point, and I have different parameters: alpha, color, fill, shape. What I'm going to do though is just use a different type of graph entirely. I will use this geom bin 2D, which does a good job of showing densities. So you can just go to this temperature variable, make a copy, and then change this to geom bin 2D, like that. And then let's go back. This bivariate histogram does a far better job of showing the distribution of observations across pedestrians on the y-axis and temperature along the x-axis. There is a concentration of points around the red circle. The red circle, which is right here. That was not visible in the scatter plot here. So the fact that the graph is one solid color of dark blue, that there are about the same number of observations scattered around randomly. This implies that temperature will not be predictive of pedestrians on its own. Next, now we have temp forecast. Oh, this looks a lot like temperature. What's the difference? Predicted daily average temperature. So this was hourly average temperature. Wait, that's interesting. This is daily, and this is hourly. Is that right? Because if I look at this, if something was predicted daily as opposed to hourly, then there should be a lot fewer points. There should be 24 points on this graph for every 1 point on this graph. That doesn't make sense. The data dictionary says that temp forecast is the daily average temperature prediction. Whereas temperature is on a hourly level. This seems wrong because there should be 24 points for every 1 point on the above graph. There should be 24 points in the temperature graph for every 1 point in the above graph. In any case, there does not seem to be this variable does not seem to be predictive pedestrians for the same reasons as temperature. Done. Next one. Oh, that's it. Okay. So, in summary, if we look back at these variables, we can see that weekday is not predictive. So that could be the least predictive, or weather hour is likely the most predictive, and temperature is the least predictive. So least predictive, most predictive. The hour is the most likely to be predictive, and temperature least likely. Task 2. Reduce the factor levels. Your assistant has reduced the factor levels of a weekday since the box plots of several weeks are similar. Run the assistant's code to consolidate weekday. Okay, so we can see here that the code below shows 3 levels, Saturday, Sunday, and weekday, instead of 7 levels. The weekday was regrouped to be either a Saturday, Sunday, or a weekday. Your assistant also recommends reducing the number of factor levels, weather, and prepared some code to do so, but requires your direction. Evaluate the relevant issues of the weather variable with regard to the business problem. Then reduce the number of factor levels to 5 or fewer. So here's the weather variable. As was pointed out from the earlier box plots, the levels of fog, sleet, snow, and wind have few observations, which implies that they should be grouped together into simpler groups. And the example below creates a new level and eliminates 2 existing levels, old level and old level 2. Replace the items in all caps with your choices as needed. Copy and paste as needed. So if weather is equal to, so I guess how do I want to group these together? Like simply I could do day or night. You know, there are ways that this could be done. Simply, we could group into day or night, or we could use good weather or poor weather, because let's try instead a middle. These would be too simple for our problem of taking into account the time of day as well as the weather conditions. And so we will use these groups. Let's just make a simple table. So let's say old level, new level. So let's just put clear day, cloudy, partly cloudy. And then we'll just put into good weather or a nice day. And then if it's clear night, partly cloudy night, we say nice night. And if it's fog, rain, sleet, snow, wind, say bad weather. So let's just see. Clear day, check. Clear night, check. Cloudy, check. Fog, check. Partly cloudy day, partly cloudy night. Rain, sleet, snow, wind. Okay, so the way to do this in R will be to do. So I have to make this a little bit more manual. So if this is clear day, nice, and then clear night, partly cloudy night, and then fog, rain, all these other things. So we'll do. So if you wanted to see how to do this, you could look at the base R cheat sheet and look at the in function right here. So this vector is in this list. It's asking if the elements are in a list, and this is under selecting vector elements, because that's what this DF weather, levels of DF weather, this is a vector. Oh, this is actually a character, so I need to convert it. So I'll do df weather is equal to as factor df weather. And that's just because when I loaded the data for this video, it was in a character format. You shouldn't have to make that type of change on the real exam, but it's always good to have a backup in case there were some technical issue. Okay, so then if you were to look at this, you can see that this is a vector, and so that's why you're using this df levels in this vector. Fog, rain, sleet, snow, or wind. So then I'll go ahead and run this. And that's giving me an error. Why is that an error? So there's that bracket and that bracket. So this should say bad weather. Alright, so now if you look at the levels, see that they're either one of these groups. And you could even do this. Insert column right, number of records, and then that's this number, that number, that number. As most records, so most observations are with fair weather. So this does say reduce them to 5 or fewer. So what I would maybe like to do is also look at the value of the target variable at these different levels, you know, before grouping together, because you don't want to do is group together factor levels that have a different value of the target variable. So the way that I'm going to undo that is I'm just going to press run all chunks above, which will sort of restart this weather variable. So if I look at it again, I can see that I'm back here. And then if I look back at this plot, you know, I can see that, you know, clear night, fog, partly cloudy, except for maybe rain. These are all low, like the median is practically zero, practically zero, practically zero, except for rain. So I would actually put rain in its own class. So I'll do like, I'm going to do this. If it's in rain, then I'll just leave it as rain. And I really could have saved myself time by not adding in this extra column because they already give you me the counts here. All right, so let's just delete this and then insert rows below. Rain, rain. Rain is put into its own group because the pedestrian's value, mean, median, is higher than fog, sleet, snow, or wind on the box plot from task 1. In general, it is bad practice to combine factor levels which have a different mean, different value, different median value of the target, because this loses information. This throws out information. Okay, the next question, consider transformations of the target variable. Your assistant has prepared code defining 3 different versions of the hour variable. Hour 1, a numeric integer variable with 17 values. Hour 2, and hour 3. So recommend which hour variable to use for decision tree. Justify your recommendation, including consideration of the business problem. So define 3 different versions of the hour variable. Hour 1 is numeric integer from 6 a.m. to 10 p.m. Hour 2 is a factor variable with levels from 6 a.m. to 10 p.m. Hour 3 is a numeric variable from 0 to 8, measuring the number of hours. Plots of pedestrian against each of the hour variables. Okay. So hour 1 is numeric and has an increasing and has a change from increasing to decreasing. This means that a decision tree could model using different cut points in the nodes. For example, you could have one right here, you could have one right here, and you could have one here. For example, the red lines show where a tree could make predictions of the average of the mean of pedestrians for these regions. And then here I can see that this is a factor. Hour 2 which means that the tree could, model these different levels as with our 1. However, the result would be more complicated to interpret because there could not be a greater than or less than sign, such as 10 less than or equal to our 1 less than or equal to 24, but would need to have a rule like our 2 is in 10, 11, 12, 13, up to 25. For business purposes, this would be complicated to explain. And then finally, our 3 is numeric, like our 1, and it is also monotonic, which means they know what monotonic means for trees. So what else was this project at? So recommend which hour variable to use as a decision tree. Okay, recommend which hour variable to use for a GLM. Your recommendation may or may not be different from that of a decision tree. And then, so this is recommended for the GLM because it only requires one coefficient to model. A GLM changes the mean of the response according to the value of the hour variable multiplied by the hours coefficient. This results in a straight line. There is another option. Another option is to use a quadratic term, hour 1 squared, which would allow for a parabola like this. That's not a very good parabola. Like that, as shown by the green line. And to make these, and just to make it easier for the grader, it's a good idea to right click on this image and then press insert caption. And it'll say figure 1, red decision tree, green GLM quadratic term. Or let's say GLM hour 1 squared. And that adds this nice caption underneath the image. Your assistant has also prepared code defining 2 different versions of the temperature variable. Temperature 1, temperature 2. Recommend which temperature variable to use for both a decision tree and a GLM. Your recommendation must be the same for both. Justify your recommendation, including consideration of the business problem. Okay, so we have temperature 1 and temperature 2. Oh, well, first of all, I have to choose which one. So our tree is hour 1, right? Yeah, hour 1, and our GLM, hour 3. Okay, and then repeat the process for the temperature variable. Define two different versions of the temperature variable. Temperature 1 is a numeric variable representing the hourly temperature. Temperature 2 is a numeric variable representing the hourly temperature. Temperature 2 is a numeric variable representing the predicted temperature. Okay, so the first thing to note, so this graph shows the average pedestrians against the, what is the temperature? Actually, it's the hourly temperature in degrees Fahrenheit. This graph shows the same thing, except it has confidence bands around the average. This graph shows uncertainty bands around the mean. A mean is a summary statistic which takes values, many values, and combines them into one. The gray shaded areas get wider for lower temperatures because there is more variance here. So as we can see, so you can see that this variable has a lot more variance. Again, this is the predicted daily average temperature, and this is hourly temperature. So it doesn't really make sense here because we would assume that there are 24 hours in a day. So yeah, the temp2 variable, which should have fewer observations because there are 24 hours in one day. However, the data dictionary is mislabeling this. It appears that this is the hourly predicted temperature. And then when we look at this, we can also see the confidence bands are wider. The confidence bands are wider on the predicted, which means that the result is less reliable. And this is also not as useful for the business problem because of what we're trying to model. Well, I guess you have to ask yourself. The business problem is the actuarial consulting firm has been hired by a national retail firm to help them understand the factors that affect pedestrian activity. So they really want to understand, how the weather would impact the number of people who go to the stores and ultimately the amount of sales that they get. When considering new locations from stores, insight into how the weather affects pedestrian activity would be useful. So just say, when deciding whether to use the actual temperature or the predicted temp, we went back to the business problem, which is helping to increase sales for stores by allowing managers to understand the effects of weather and time. So if I was a customer, to put ourselves into the shoes of a customer, we would imagine that the predicted daily temp would be sufficient because people look at the weather once in the morning when planning out their day. if they see that the weather is predicted to change, then they will, change their plans. If they see that the weather is predicted to rain, then will not go shopping. If they are already at the store and it starts raining, then they, will likely continue shopping. For this reason, we recommend using the predicted temp instead of the actual temp. Justify recommendation including consideration of the business problem. Run the code to create the temperature new variable as recommended and remove the other variables related to temperature. So we're saying temperature new is temperature 2. This question was very difficult to grade because there was a technical error in the RMD file. This was the message that was sent out to people after they'd taken the exam. This message is in response to the situation you experienced while taking the December 2020 exam. After a review by the SOA staff teams and volunteer leaders, we determined that for candidates that chose hour 2, the factor variable for hour tree in task 3, the code provided in task 5 did not work, and the section of code indicated not to change the code. The SOA has adjusted the grading of this version of the file accordingly to take this issue into account, and our final score will reflect these adjustments. So this was an error, in the RMD file. Some people did comment this code out and then left in the comments that it didn't run successfully, which is the best thing to do. If you ever do encounter a technical error like that, just explain it and move on. Don't spend a lot of time on it, and that will be reflected in your grade. Finally, it is worth noting that this was a really long question, and there are other ways that it could be answered correctly. In this solution, I do talk about this relationship, hour 3, being a linear relationship. However, the official solution says that that's not a very strong justification for using it. Task 4, 9 points. Consider transformations of the target variable. Your assistant notes that the target variable, pedestrians, is skewed and therefore recommends transforming it. Explain how transforming the target variable has an effect when fitting a decision tree model. So they're just asking, well, let's look at the target variable distribution. We look right here, we can see that it is right skewed. Let's get a big histogram and put that into the report. Task 4. There it is. So a decision tree works by partitioning the feature space into rectangular regions and then predicting the mean of the target for each region. This asks a series of yes or no questions to each observation, and based on this, based on the answers, it puts them into different buckets. The target variable, pedestrians, is right skewed, positive. So because a decision tree relies on the mean of each bucket, and means are sensitive to outliers, the decision tree will have better performance if we apply a skewness correction via a transformation prior to fitting the model. And several of those transformations are shown here. So log, square, so here's the log. Taking the log only makes the skewness worse. Your assistant has provided code for several choices of transformations. Supplying code for these: no, log, etc., square of, square root of, inverse of. Recommend which transformations of the variable from the list to use for a decision tree model. Justify your recommendation. So yeah, this one obviously doesn't work. We don't recommend this. What about the other ones? This one is the square. Actually, I should say this doesn't make the by causing a right skew, a left skew instead of a right skew. Taking the square causes a right skewness to increase. We do not recommend this. This one, taking the square root, helps to correct the skewness. The skewness, the skewness is high when the variable is asymmetric and low when it is symmetric. The square root causes the distribution to be approximately between the values of 0 and 50. If you were to look like right here all the way over to here, it is approximately symmetric with a median and a mean that's equal to about 20. So we recommend this as the transformation. And this one is the inverse, which just makes the skewness even worse. So recommend which transformation of the target variable to use and justify. Okay, done. Note to candidates: you will not use a transformed target variable in most modeling tasks in this exam. You will use the untransformed original pedestrians as the target variable unless you are directed otherwise. Okay, task 5. Build 2 trees. Ooh, this was actually all task 5. This was task 4. So this should have been in task 3. It's important to get this right because this is how the grader will look at it. Oh, and look at this. When I moved the graphs, it did not move these annotations, which is quite frustrating. So I will have to move these. Ooh. You know what? I'll just redraw them. So it was just this red one. And then this green. Okay. And this goes into task 4. Okay, build 2 trees. Run the code chunk that partitions the data into train, test, and holdout sets. Right here. The 2-step process below partitions the data set into 70, 30, 10 subsets. First is 70, 30. Okay. And then 30 becomes 20 and 10. Okay. Then create similarity named dataset for all. Remove unneeded variables. Check means of untransformed target variable. The means are all about, actually the means are quite different for the holdout set. $9.75 versus $9.60. Your assistant has prepared 2. Okay, so first of all, so we created. So in order to verify that our models will generalize into new data sets, we used a train test set approach with a final holdout set. We first split the records, the data, into 30% and 70%, which is used for training. Then we split the 30% into 10% and 20%. So the 10%, which will be used 20%, we will use to test the choices of our model parameters. We do notice that the mean varies across these data sets. It would be helpful if it showed the which data set this was. So this is all records, and then training, testing, holdout validation. So we do notice that the mean varies across these data sets. The validation set has the smallest sample size, and also has a higher mean than the others. This is due to the random, assignment of the records. So the results could change if the data were run using a different random seed. Okay, your assistant has prepared 2 tree models. One uses the untransformed pedestrians as the target variable. The other uses the square root of pedestrians as the target. Run the code provided to fit each tree. For each tree, state the predicted median count for the following levels of the original variables. Okay, so they want you to say at hour 6, temperature this, temp forecast this, weather this, what the prediction is. So let's look at this first tree. Okay, So we have to look at hour 6. So let's grab the highlighter. So is hour equal to 6? So the first variable here is weather. So it's cloudy, so this is bad weather. So that means here. And then our tree less than 6, yes. And our tree less than 7. Yes, so that makes a prediction of about 69. First tree of 68.4, which represents, based on the hour being less than 7 and the weather being bad. This group, this branch, represents this leaf. 3.74% of the observations in the data. And then this other one at hour 15 so in hour 15, temperature 5, weather rain. So this will also be bad weather, but now our tree is greater than 10. And it's 15, so it's asking, is our tree greater than or equal to 19? If yes, go left. If no, go right. So go right, and then temperature is, remember we're using temperature forecast, so this is 64. So their temp forecast is 86. So if it's less than 64, you go left, but this is greater than, so I go right. And this is 986.6 pedestrians. Based on the hour being greater than 10, but less than 20, then 19, and the temperature being new. And the forecast be greater than 64. This represents 0.7% of the observations. Okay, now we have to do this for the other tree. And this is using the square root. So right away, if we look at the predictions, we'll notice that they're scaled down because they're basically the square roots. Like, the square root of 70 is about 8. And if you look at the node here, you can see that it's like between 6 and 8. So we have to draw these two graphs again. So for hour 6, remember it's bad weather. So yes, hour tree less than 21. It's equal to 6, so it's yes, less than 10. Hour tree less than 7. Yes. And then this other one, hour 15 is not greater than 21. And then hour tree greater than 10, or less than 10. No, it's greater than 10. And then hour tree, hour is 15, so that's not greater than 19. The second tree, which has the log, the square root, 7.573, because of the hour, because of the bad weather hour. This represents 3.74. Notice that the square root wide, and so if we take the square, so what's 7.5 squared? We get about 56. Get 56.7. 56.7 is fairly close to 60. And then the second one is 20.12, or when squared, 404.8, because of the hour, bad weather. 7% of the records, and it is different, is lower than the prediction in the first tree. Your assistant notes that the RMSE of the model using the transform target is lower of the two and recommends that model. Critique your assistant's reasoning. Well, what we're actually talking about, the first tree uses the untransformed target, and so the root mean squared error will be on a higher scale. For example, the first tree ranges from about 60 to about 1800. So the RMSE takes the square root of the square joules, and the will be higher. So what does it mean if you take the square root of a square? It just means that you always have a positive sign, but the residuals will be greater because the numbers are bigger. So the assistant is wrong. Consider a random forest. Your assistant recommends, well, actually, let's look at the, so we do have the RMSEs. 531. RMSE of tree 2. It's 8. 4, 7. Well, what if we take, this takes the square root. Wait, this is interesting. So the first one takes the mean of, so it just takes the square root of the mean of the square of the residuals. And the second one takes the square root of pedestrians. Okay, so if we wanted to fix this, we couldn't, because they're basically different models. So this is an apples to oranges comparison. However, oh no, what we could do is we could take tree 1, and then to the square root of the predictions and the square root of this. Or we could take this one and then square the values of the predictions and then calculate the RMSE. So if we do that, there are two ways that we could fix this problem. Take the square root of the pedestrians and the square root of the first tree, or take the square of the predictions from tree 2. We choose to use the first approach, and note that the RMSE is 8.579, which is worse than the second tree. And just to be safe, we can also do the second step. So we'll take this one and we'll square it. So we'll just square, the predictions of we'll square the values of the predictions. The second approach leads to an RMSE of 53598 for tree 2, which is worse than for tree 1. Right, so like if we use the first method, so these are conflicting results. So because if we do this, it says that the RMSE is 8.5 for tree 1. So that means that this one's better, tree 2 is better. And if we do it the other way, it says that RMSE for tree 2 is 535, which is worse than tree 1. So I would say these are conflicting results because this is an apples to oranges comparison. Okay. What did the question actually say? It had just said critique the assistant's reasoning. It didn't say that you have to choose which tree is better. Task 6, consider a random forest. Your assistant recommends not using a random forest because it requires too much computing power. Describe 2 other considerations when dealing with whether to use this method. So random forests are ensembles of decision trees. So if I just think I have to fit a lot of different decision trees, so it will take longer to. So in addition to more compute resources, random forests are more difficult to interpret because there are hundreds of trees used. And what else? In addition, well, there are two parameters that you need to tune: the number of trees and the number of variables to consider at each split. But most of the time you can just set that at the default of the square root of the number of columns in the data and then just tune the number of trees. So random forests are difficult to interpret. They can pick up variable interactions and transformations and fill in missing values, just like decision trees can. Describe 2 other considerations when deciding whether to use this method. So another would be, that's a good question. Well, let's look at our actual tree. I think another thing would be to just talk about the hyperparameters. Another consideration would be how to tune the hyperparameters for entries and mtry. And you know, a good thing to do a question like this is to do question mark random forest. And if that library isn't loaded, you can just load the library random forest, because that will be installed on these computers, even if it's not being used on the exam. And then do random forest. And then you could just read the documentation and get some ideas, like uses the algorithm and an optional data frame. So it looks at mtry, entry. Yeah, so another thing to consider is the way that you're training. You know, in this case, you're doing, which can lead to overfitting because, you know, of the small size of the validation data set. We saw earlier that the mean of pedestrians was, you know, significantly different. I'll just say it was different in the validation set than in the training set. And so if we, you know, spent a lot of time tuning a model and then tried and then applied it to a new data set, we risk overfitting and as a result having poor performance in real life. That is another consideration. Okay, and then task 7, fit a generalized linear model. Explain why Poisson is a reasonable distribution choice for this problem. The Poisson distribution models the count of models count. The pedestrians is the number of people who walk by during a given hour. And so this can be understood as a Poisson process. This also matches the distribution because it is positive, discrete, and right skewed. State 2 other reasonable choices of distribution. Explain why each choice is reasonable. So we could also use a gamma or an inverse Gaussian, because these are positive and right skewed. They are continuous rather than discrete. And so the predictions would come out as, you know, real numbers instead of integers. We could, well, in this case, however, the client is only concerned about inference and does not need to use the model to make predictions. Run the code for GLM using a Poisson distribution with log link function, okay? and then just copy all of this in. And you'll notice that there's currently a glitch with this version of Microsoft Word and R, and so this is not copying as text. So my solution is to use the keyboard shortcut Windows Shift S to take a screenshot. On the real exam, this will not be a problem because the parametric computers use an older version of Microsoft Word. Okay, so, and then we have to fit another type of model using a different distribution than Poisson, but still using log link. So distribution, so let's try the gamma, and then compare that to inverse Gaussian. Just so that we can say, well, no, it says only try one more, so we did. Okay, so if we just look at log likelihood, 519 versus 7. So the log likelihood is a measure of how well the model fits the data. This is the log of the probability of generating these pedestrian counts given a conditional on the data. This is lower 519 than the gamma, than the GLM, which has a gamma response family, which is 780. It is interesting to note, which implies that the Poisson is the best choice. It is worth noting that the first model is that the second model is overfitting or underfitting because the training error is worse, higher than the testing error. Using a model or increasing the variance and decreasing the bias of this model by adding in more variables or creating new features would likely resolve this underfitting. Yeah, you can see that by here as compared to here. Recommend which GLM to use. Justify your recommendation, including consideration of the business problem. So remember, the business problem was simply to understand how time of day and weather impact sales. The second model has less certainty around the weekday coefficients, as is shown by the high p-values. This means that any results are subject to change if the data changes. So this model has p-values that are all less than 0.001. We can also, let's see what else we have. Well, we don't look at the plots. We could also look at the diagnostic plots. This is 8 points. So could you plot GLM log link 2 and compare that to plot GLM compare that to this one. So we look at these residuals versus these residuals. You can see that there is more of a pattern. These are further from normal. These are closer to normal. And then let's add a caption. So this is the, insert caption. Let's just change that. That is rather annoying. The Poisson, the GLM with a Poisson family left has residuals, has deviance residuals, which are closer to being normal than the GLM with the gamma family. This shows that the Poisson model is a better fit to the data. Consider an interaction, 6 points. So this should only take about 15 minutes. Your assistant has prepared code to help explore for a suitable interaction. Recommend an interaction term where at least one of the two variables is a factor variable to include in the GLM. Justify your recommendation, including consideration of the business problem. So first of all, an interaction is when the impact that a variable has on the target changes on the... An interaction is when the impact that a variable has on the target changes depending on the values of another variable that is in the model. Now let's look at the code. Your assistant has provided the following code for exploring an interaction. This produces scatter plots of a continuous variable by the target, colored by a factor variable. Replace continuous with the name of a continuous variable. Okay, so sort of before doing any of this stuff, just think, what two things might be interacting? If you're going shopping, you might think, oh, I should check the weather, and I should also see that there's gas in my car so that I can drive there. Or I would, make sure that I have enough time, that the stores are open. So I would look at the hour, and I would also look at the weather. So one thing to look at would be, X would be hour. We're using data all, so I actually don't remember which variables we're using. Okay, so so continuous will be hour tree, and then color will be, well, if we wanted to look at, the hour and the weather, well, that wouldn't work because weather, okay, so this shows that so the x-axis shows the value of hour, the y-axis shows the number of pedestrians. Actually, that's not right because this is okay, so it's showing you, actually don't understand. Okay, so this plot shows you the scatter plots of the hour against the number of pedestrians. So you can see, for instance, when it's a nice night, the hour is always greater than like 15, because otherwise it wouldn't be a night. So that's obvious. And then we can sort of see, like, when it's a nice day, the number of pedestrians is typically higher rather than when it's bad weather or raining, the number of pedestrians doesn't really change depending on the hour. It's always sort of flat. And if you think about that, that sort of makes sense. If it's like gray and cloudy, you might look out the window and say, yeah, so there is an interaction between hour and the weather. when deciding to go shopping, people will think about if they have enough time to get what they need before the store closes, and also if the weather is nice. The upper left graph shows sunny days and cloudy days. Here there is a wide range of values. Sometimes because sometimes there is a lot of traffic. Other times there is not. During bad weather or when it is raining, there are about the same number of pedestrians at any point in the day. This makes sense because during cloudy days, it is not always easy to tell what time it is. The morning may be dark because of clouds and thunderstorms. Okay, that's one interaction. Recommended interaction term, where at least one of the two variables is a factor variable. To include, justify a recommendation. Okay, and now let's just think of, so let's try just fitting this into the GLM. If this works, we don't need to even look at another one. So let's say we use hour 1, I think. No, our GLM and weather. And then our family was on. So that's that. So as you can see, the interaction term does have a p-value that's less than 0.001, which means that it is a significant interaction. It is improving the, well, we can ask, is it improving the result of the model? If we wanted to look at the RMSE, we don't have enough time, so we'll just say that. If we had more time, we would look at the RMSE of this model and see if it was lower than in the model without the interaction. This interaction is effectual or legitimate, is present in the data as because the p-values on the weather, nice, night, hour, GLM, and weather, bad, weather, hour, GLM, and weather, rain, hour, GLM are all less than 0.01. Weather, nice, night, hour, weather, bad, hour, and weather, rain. You could all make these bold. If we had more time, then we would look at the RMSE of this model to see if it was lower than that without the interaction. Next question. Interpret the result of the coefficient from the interaction term. So the coefficients here, well, we have the coefficients sign tells us if the variable is increasing the number of pedestrians or decreasing. it. So we can look at these levels. Well, first of all, we have to consider the reference level. So the reference level, we looked at weather, right? We had 4 different weather categories. And here you notice that there are only 3 interaction terms. There's nice day, nice night, bad weather, rain. So there's rain, bad, nice night, and new day. So nice day isn't there. So this one, this is the reference level. Which these other coefficients are referencing coefficients are comparing. So this one, weather, nice night, hour GLM, this one is negative. Weather, bad, and then weather, rain. This one is also negative. This one is negative. So, if we had a, let me just sort of doodle here. We have something like e to the beta 0 plus beta 1 x1, and then we have the interaction term beta 1 2 x1 2, which is the interaction term. That one, so that the sign of this coefficient tells you the percentage change in the target for that specific interaction term. So you could just say what we would want to do is take the exponent of these coefficients. Exponent of GLM.interact, exponent of coefficients of GLM interact, right? And we do that, and then we subtract 1, we get the percentage change. So we look at weather, nice night, hour. 12% lower. This one is weather, nice night, weather, bad, weather, nice night, hour. Yeah, that's 12.6%. Weather, bad, hour, it's about negative 0.055% lower. Rain, at 7.5% lower. And how do you say that? Well, for a Poisson log-link function, the model is the mean of the Poisson distribution is a function of the data and the coefficients. You could say mean is equal to exponent of beta 0 plus beta 1 x1 plus beta 1 2 x1 2. Yeah, and remember the audience here is like the graders team, and so they wouldn't expect you to write this out in LaTeX format or do anything really fancy like that, where x12 is the interaction between x1, x2, and beta 12 is that coefficient. So to find these values, we took the exponent of the coefficients and used them below. So this is 12.6% lower. So the slope, oh yeah, so that's how you, so this is the slope of nice night, the slope of the hour GLM, or the coefficient on our GLM is 12.6% lower during nice weather than during nice nights, than during nice days. The coefficient on our GLM is 0.005% lower during bad weather. The coefficient on our GLM is this percent lower during rain. So this means that the number that pedestrians let's not try to spend too much time on this because this is just a 6-point question. Task 9, 9 points. Select features. This should take about half an hour to complete. Some features may lack predictive power and lead to overfitting. You will select features using BIC for your model from task 8, including your selected interaction term. Forward and backward selection are among the available techniques for feature selection. Describe forward selection and state the differences between the two techniques. Forward and backward selection are both methods of choosing which variables to include in the GLM based on the penalized log likelihood. And then to remember the formula, just look at the documentation for AIC. And here you can see the formula. So this is 2 times L plus K times the number of parameters. So K is the number of parameters in the model. And so because you have -2 here, when you have -2, so here's the formula in R. You can see that it's using K is equal to the log of n row of train, which in our case is about 9, which is greater than 2. So when K is greater than 2, then you have a simpler model. Then BIC favors a simpler model than AIC, right? So AIC, when the log of the number of parameters, the number of observations in the training data is greater than 2, BIC favors a simpler model than AIC does. Both, yeah. So forward selection begins with no parameter, no variables, and only adds variables which improve the BIC. Backward selection begins with all variables and only removes variables which improve the BIC. And when it comes to remembering is higher is lower, just remember that you maximize likelihood and you minimize variance. And so this formula is using negative log likelihood. So if this number is really high, like log likelihood is 10,000, then this number will be really small. And you know that the log likelihood should be high because you want the likelihood to be high. And so when you maximize the likelihood, you know that lower is better. So you can say this lowers the BIC. Yeah, and you can say that both directions continue iterating until the BIC stops improving, stops getting lower. So it's possible that for forward selection, it is likely that a simpler model will result because the BIC will stop improving while there are only a few variables. On the other hand, with backward direction, a complex model is more likely to result because the algorithm will stop as soon as removing variable will not, as soon as removing any variable will not decrease BIC. And what's the next question? Recommend which technique to use. Justify your recommendation. Well, we recall from the business problem that the goal is inference on the pedestrian activity, and predictions do not need to be made. For this reason, we favor a simpler model, which will be easy to interpret. And so we recommend using the forward selection. Determine which features should be retained using only the recommended technique. Run the step AIC function from the mass package to make this determination. So let's look at the code. The following code executes the step AIC procedure, allowing for forward or backward selection. An empty GLM is needed to implement step AIC. Replace the distribution below to match your choice from task 7. So let's use the Poisson. If you chose a different distribution, then it would be, reasonable to use that if you could justify it. And of course, it's really important that this GLM have the same family and link function that the other GLM have. Otherwise, it would really be creating problems. Also, loading the mass library will often cause conflicts with the tidyverse libraries, and so if you do get errors with libraries, the simplest approach is just to reload everything in R and then avoid loading the mass library unless you really need to. Okay, so we're just going to use forward selection. So we'll just copy this output. So we see that it starts with just pedestrians follows 1, which is shorthand for an intercept only model. And then it adds this our GOM. And this column here says AIC, but it's actually BIC. So we see that it goes from, so you can see how this is working. It starts out with just the intercept only model, and then it looks across all the variables, and it sees that our GLM has the lowest BIC, so it adds that. And so the next model is just pedestrians with our, and then it looks across all the BIC values, and it finds that weather is the best, so it adds weather, and it keeps doing that. So it says weather hour temperature, weather hour temperature weekday, etc., until hour GLM weather weekday. And so then it's just using all the variables: hour, weather, temperature, weekday, precipitation, the interaction, hour, weather. So we do have to take a screenshot of this. The stepwise, the forward, the algorithm begins with intercept only model and then finds that adding our GLM will decrease the BIC, and so it adds this. Then it finds that weather will further decrease it, so adds weather. Then it continues until all variables are added. Finds it adding our GLM, make that bold, and then interpret the result of this first step of the AIC function output. So if we just looked at the first output here, right here, that's what we would see. And then I would just take the highlighter. This is optional. You don't need to add the highlighter, but if you wanted to, you could do that and then point to this BIC value. And then here it finds that weather is the weakest. Weather has the lowest AIC. That's weekday, that's not weather. Weather is right here, and that's that. Task 10, recommend a model. Recommend a GLM for this business problem from among those fit in tasks 7, 8, and 9. Justify a recommendation both quantitatively using 𝐕𝐈𝐃 as a test metric and qualitatively. So whenever I'm looking at comparing models, I want to create a simple table that will show the model, could even show the task, model, and then the train RMSE test, RMSE. 7 and 9. We are talking about GLMs for all of these, and so up to task 7. So here's the GLM. So we have the Poisson distribution. We also fit the gamma, and so this first one was the Poisson. So this has a log likelihood, log link GLM1 train RMSE. So train is 512.273 and test is 519.459. And we already saw that this was better than the gamma. So this is a Poisson, GLM with Poisson family log link. And then in task 8, we added the interaction term, hour and weather. So when we did this, well, there's the AIC. Where's the RMSE? So here's the code that does this. So even though this wasn't in the template exactly, it's quite easy to make this change. Just put this in here and change this to GLM interact. You're going to predict based on GLM interact, and then it's still data train pedestrians, and then this is also GLM interact, and then change this to predicted train GLM interact, and that's the model prediction. So change it there, and then change it here. And we'll see that that is 508.2829 rounded. 2897. And then test is 516.618. So that one is definitely better. You just make this wider and then wrap the text. And then finally in task 9, we had the step 𝐕IC function, step 𝐕IC model, which was the same from task 8, right? So you just copy that down. And then I can make this nicer to read, copy this picture. So to compare, to decide on which model to choose, actually, let's go back to the project statement just to make sure we're doing exactly what they want. Recommended GLM for this business problem. So on which GLM to use as the final GLM, we looked at group needs the RMSE on the training set and testing sets. This is different from using the log likelihood or AIC/BIC because these are only based on the testing set. The results below show that the Poisson, that task 7 shows that the Poisson family and log link are the best choices for response family and link function. Then in task 8, we found that adding the interaction between our GLM and weather improved the performance by reducing the error substantially. Finally, we confirmed that this is the best choice by running forward stepwise selection with 𝐕IC and returned the same model. Next part, recommend a model for this business problem between the GLM just recommended and the decision tree using the untransformed target variable from task 5. Task 5, let's go up for task 5, building 2 trees. So this is the one that doesn't have the transform. I remember that because I can look at the target value and see that it's really high. And they say the model would recommend a decision tree with the untransformed target. So should we look at the no, we didn't look at the error, so I want to go back up to task 5, and I'll do that by going Control F, and then task 5. I guess I have to scroll up. Task 5, build 2 trees. There's a train test split, and so it was this tree 1. Here's the RMSE, and it doesn't calculate the training RMSE for that, but that's okay. Okay, so that's 531 tree. Let's see on test set 531, 597. So if we compare that to, let's just make sure that this is the right one. Yeah, this is just RMSE. This isn't that other like transformed version of RMSE. The decision tree from task 5 had higher RMSE, that the performance was worse than the GLM at 531, 597 instead of 516.618. For this reason, we recommend using the GLM. So although the objective is not to make predictions, having having higher performance indicates that the results will be more real representative to real life. A decision tree is easier to interpret, but if the tree is making bad estimates, then this just, makes bad estimates easy to interpret and does not help the client to increase their retail sales. So I do notice that in the SOA's answer, they found that the decision tree had better performance, and so they chose that. However, that's not what this question is asking. It's just saying, look at the results of your two models, and based on those, then make a decision. So it could be that earlier on in the report, there was difference in the way that the data was transformed or so forth, and that results in a better model. But those two questions would be graded independently. So if you have extra time, it would be a good idea to go back and to look into that. But if you don't have extra time, just stick with what you have and then explain it, justify your answers really, really well. Lastly, run the recommended model in the full data set and use it in the executive summary, regardless of the results from task 11. So all that we have to do is just change the input data. So we'll go back to our interaction GLM right here and then train it on the full data set. And this also says the RMSE for GLM given in task 7 can be applied to other models in the space below. Yeah, so like right here, this would be a good idea to include this code down there so that the graders will see it. Otherwise, you could just be making up those numbers. And then here they say copy the selected model and retrain it over the whole data set. So what is the name of the data set? Remember, it's just DF. However, we want to be careful that we use the version of the data that has all the transformations that we had. Data must be a data frame, environment, or list. Okay, let's look at DF. This is a function. Yeah, so that's what I'm talking about. So how do you fix this? Well, go to the training and test set right here. And so this is using, DF pedestrians. So to recreate the data frame, I'll go to run and run all chunks above. And then this will just recreate that data. Oh, I see. It's right here. It says data.all is equal to df. So perhaps I could use data_all. Yep. Okay. And then we want to copy the results of this. There it is. And if you were to compare the standard errors here, you'd see that the standard errors are smaller than on the other one. Like let's go up to right here. No, that's the gamma. This is the GLM interact. If you look at this standard errors, these standard errors here, you compare them to the final one. So if you look at that, like standard error 4.88. I guess the standard, yeah, so the standard error is smaller on the full data set. And I would just like add an annotation around that. So I'll just do insert shape box. No fill, shape outline, red, do like insert caption. So these were from the training data. Insert caption. Okay. And then just like add a summary. And this is actually from task, this is still in task 10. So take task 11 right here and move that down. Lastly, we retrained the GLM with the interaction over the entire data set. This has a larger sample size to estimate the coefficients, and so the standard errors are smaller. The next is assess the model selection performed in task 10 quantitatively using the holdout data. You might be somewhat surprised by this question because it seems like we've already done that. Well, no, we haven't, because there are 3 data partitions: the training set, the test set, and then the holdout set. So we looked at data.all. Okay, so here, look, I see this is data.all is using all. So this is data train. Data train is using, 70%. So that used the data test. Okay, so when I look at that, when I look at this GLM, I actually wanted to use the training set. So this is run the recommended model on the full data set. Oh no, okay. So it says run the full model on the recommended data set for the use in the executive summary, regardless of the results from task 11. Okay, so now we'll go back to the holdout set. And use it on whatever it's called, data holdout. So GLM interact holdout. So now that we've done the model selection, you might think that we're done. And then this question 11 says, validate the model selection. Assess the model selection performed in task 10 quantitatively using the holdout data. Well, if we looked at data all here, we saw that we used 30% for the training and the testing and the holdout, and when we use 70% for training. So there's still a 10% of the data that hasn't been touched. It's been kept in a vault in the back, and now it's time to put the model against it to see as a final test if the result works. So to do this, we just have to take our interaction model and put it against the holdout set. So because I've changed the names earlier on, I'm just recreating this, and I'm using data train like that. And then for here, I just need to change the name of the data. So the way to quickly do this is to use a copy and replace. So I say data train and then replace data holdout. And then check this box that says in selection. Replace. That was only one occurrence, so let's do that down here. In selection, replace 2 occurrences. Okay, so here's the holdout. Don't need this. And then I can see that it's 542. 542. So 542.1039. So we already trained the model and chose the best link parameters using the testing set. Now as a final step, we use the holdout set, which represented 10% of the original data, to test that our model works. This proves that in real life the results will be as effective as they are in this study. The RMSE is 542, 10^9, which is slightly higher than in the testing set. This is because we have already, chosen, evaluated several models against the testing set. And so it, no longer was a blind holdout validation set. This small amount of overfitting is normal and that's enough. Okay, finally we get to the executive summary. 20 points. Executive summary. Your executive summary should reflect the info provided from tasks 1 to 11 as relevant to the client. Your executive summary should include a problem statement and a coherent explanation of all the steps leading to your recommended model and conclusions. Interpret the results of your final model in a manner that will provide useful information to the client. So first of all, we just need to sort of restate, the business problem. So let's go back to the initial business problem. So our actuarial consulting firm has been hired to a national retail firm. So one way that I could structure this is just by saying to national retail firm, and then from actuarial consulting firm. And the problem was helping them understand pedestrian activity so that they can optimize, their existing stores. They have locations. When considering new locations across the U.S., they want insight into how the weather affects pedestrian activity, so it would be useful. As your stores. So I'll just open up by saying, as your retail chain continues to expand and open more stores, we can help you to determine the most profitable locations. Yes, so your experts have informed us that weather and time of day, for new stores, yes, for considering new locations, they want to know that weather is key for determining how sales, how much traffic, foot traffic, these stores attract. For your existing stores, understanding how pedestrian activity varies by time of day and day of the week will allow you to optimize weekly ads, coupons, promotions, and staffing. So using predictive analytics, we present to you the findings of how you can. We present to you these findings, which will help you, which you can use to grow your business. So we conducted a data analysis using data from, where's the data from? the city of New York. And from 2017, 2019. Let's just say you can be sure, you can depend on the accuracy of these results. We conducted a data analysis using data from the city of New York from 2017 to 2019. And how many records were there? There were 11,000. With over 11,000. It's nice to use precise numbers. 11,373 observations of. I need to zoom out so I can see the beginning of the report. So let's do split. And then zoom in, and then go back up to the beginning. The hour, number of pedestrians, the number of pedestrians in a given hour. We looked at the hour of the day, precipitation, forecasted temperature, actual temperature, and then weather conditions. We did not find, we inspected this data for errors and found none. Humans are habitual creatures who shop, during certain days of the week. However, we found that weekday by itself, the day of the week alone, was not sufficient to guarantee if there would be a lot of traffic or not. This, if the weather is bad, then people tend to cancel their plans and stay indoors. On the other hand, the time of day is extremely important. It is closely related to the amount of traffic of pedestrians who are out. So you can use this. You would like to know that during 10 a.m. through 6 p.m. are the highest traffic times of the day. And here it's saying related to the amount of pedestrians who are out. A better choice of word would be number. So how do we talk about weather? Well, shopping and spending is related to our emotions. How we feel based on the music in the store and the weather outside does impact our spending habits. Before people even enter the store, however, the weather determines if they go outside or stay inside. The forecasted weather is more predictive of traffic than the actual weather. And so we recommend looking at weather forecasts when choosing your new store locations. Be careful though, as a word of caution, is to consider the other factors at play. Using weather alone is not sufficient for predicting the amount of pedestrians who are out, the number of pedestrians out and about. Humans like things to be simple. Weather is a complex phenomenon, and you can benefit by simplifying every day down into 3 categories. A nice day, a nice night, bad weather, this is 4 categories, or rain. Phenomenon, that is the correct spelling. Weather is a complex phenomenon. Okay. So we talked about weather. Yeah, most people go out in fair weather and stay indoors during poor weather. You know, like we advise staying away from, you know, except from areas that experience heavy rainfall. No, let me say, we advise against, like, you know, marketing to walk-in customers in areas where there is continual rainfall throughout the year, such as Seattle, Washington, or places that are cold, always cold during the winters, such as Chicago or Boston. And you could use some other examples. Then we reduce the factor levels. But if you say that in the executive summary, we reduce the factor levels, they will not know what I'm talking about. Talked about, so yeah, the decision tree, choice of variable here. Yeah, so the time component, the time variable is critical to helping you to maximize revenue for your existing stores. When do people shop? That is the key question. That is the key question. We considered 3 different ways of looking at time, of thinking about time. The first is what we'll call like clock time. The second we'll call, I don't know, like time blocks. And the third is relative time. So clock time is, this is the exact time that we see on the clock. So from 8 a.m. in the morning to 10 p.m. at night. Time blocks, these are discrete, these are chunks of time, these are hours of time, such as 12 lunchtime, 12 p.m. lunch, 11 a.m. brunch. Let's put them in the other order. 11 a.m. brunch, 12 p.m. lunch, 1 p.m. coffee hour, and so forth. And the final is relative time. The number of hours from before or after 12 p.m. I think that's 12 p.m. Let's look. Is a factor variable with levels. where is that? It's in the project statement. Consider random forest, fit a GLM, select features, build 2 trees. Hour 2 is a factor variable. See absolute number of hours from 2 p.m. Absolute numbers from 2 p.m. So this considers, and 2 p.m. is the peak time, right? 2 p.m. So this is 10, 11, 12. So this is 3 p.m. So yeah, 2 p.m. is about the peak time. Depending on the type of model, we recommend using a different, we recommend using either the first or the last measure. The first has the advantage of being easy to understand and would work well for a decision tree model. This is a series of yes/no questions, which you would ask about the weather situation and day of week. The second, the weather situation, day of the week, hour, and so forth. Yeah, the last type measure is useful for linear models where you need an approximate way of measuring time. And then we want to think about the temperature. And I think I actually already talked about this. I talked about weather here. And this is the weather, yeah. So I'm just going to copy this paragraph and move it down here. So I think it makes more sense. How we feel based on the music of the store and the temperature outside does impact our spending habits. You know, cold weather keeps people indoors, while warm weather encourages people to go outside. The forecasted temp is better traffic indicator than the actual temp. And so we recommend looking at the weather forecast when choosing the new store locations. A word of caution is to consider the other factors at play. Using temperature alone is not sufficient for predicting the number of pedestrians go out and about. Okay, and then we consider transformations of the target variable. How would you explain this? Well, we know that, you know, measuring, let's just say days can either be extremely busy, you have to say, as anyone, as those who work in retail are familiar. When it rains, it pours. When it comes to customer traffic. Days when it is slow seem to drag on for weeks on end, whereas days when it is busy fly by quickly. we wanted to consider this. We considered this in our models. We considered this feeling in our models by making adjustments to the count, to the number of people who were active. If we just used the count of people by themselves, we would run into problems. Because, when there are, 10,000 people outside, then an additional, 1,000 people is not surprising. However, if there are only, 50 people outside, it is extremely unlikely that an additional 1,000 would, come about unexpectedly. Mathematically, this is known as a skewed distribution. To resolve this, to address this, to adjust for this, we tested out different adjustments, formulas for compensating for this. We found that taking the natural logarithm, actually, let's go back. What was it that we worked on? Remember, so we wanted the distribution to be symmetric, and it was this one. Taking this square. Of the number of people caused this measure to be more stable statistically. We did not use this in our final model, final result, but are including it here for completeness, for completeness. Really, what it's trying to do is just show that you can explain this really complex statistical learning theory in simple language. Then we built decision trees. We made some predictions based on those decision trees. So I would say the first type of model. So there's no silver bullet. No, they're not going to understand what that means. Every situation is unique and requires a different type of solution. There are many types of models to choose from, and each have their advantages and disadvantages. For your problem, because you are looking for simple and easy to understand results, we tested out generalized linear models and decision trees. The decision tree is a series of yes or no questions, which can be thought of as a series of rules that get applied to every row in the data. So on any given hour, the tree asks how many people are, what the weather is, what the temperature is, if it is raining or not, and so forth. And based on this, it comes up with an estimated number of people who are about number of pedestrians who are about during these types of days and times. The GLM is a method. The GLM relates the number of pedestrians to many variables at once, so that we can take into consideration the exact values of the temperature, time of day, weather, and so forth. Then it uses a formula to calculate a number of pedestrians. Yeah, so let's just look again at our tree. So, we fit two different trees. We fit two different and chose the one which most closely matched the data. And then the GLM, how many GLMs did we fit? We fit 3 different GLMs. Yeah, and then chose the one which did the best, which did the best job of matching the data. We could also think about, we did not more advanced machine learning methods because of two risks, two concerns that you would likely have. And these are, one, the amount of computing resources and IT infrastructure required, and 2, the possibility of being wildly wrong by miscalculating a result. The more complex models require more attention from the actuary or data scientist who is building and maintaining them. Okay, and then we fit the GLM, fit 2 different GLMs. Consider the interaction, and this is when I need to show them the result. So I want to go down to data.all, and then take these results and turn them into a formula. So before fitting our GLM, it would have been ideal if we had set our reference levels to be the ones with the most observations. However, we didn't remember to do that. Don't worry, it's still possible to salvage part of an answer here. The way that I would do that is just take data.all well, and then just first, just look at the types of data. How many factor variables are there? So you can look at structure, data, all, and then see, okay, there's a factor for weather, and that's it. So if I look at summary or levels, data, all, weather, see the first one is nice day. And then if I look at counts, so I do data, all, count, weather, see that nice day is the one that has the most observations. So that is the right reference class. Then just to double check, then we have weekday. Weekday is being read as a character. So if I look at weekday, I'll see that these basically have the same number of records in each. And so it doesn't really matter what the base or reference level is. So I would just add a comment here that says, checking that the reference level are the ones which have the most observations. Okay, and then, run this, and then look at the summary. And now I need to get these coefficients into Microsoft Excel. So I'll just do paste. Might take me a second. And then I get rid of all of this. And then I don't need this. So I just have the estimate. So this is beta, and then this is exponent of beta. And then I need to just round these numbers so that they're easier to read. And then the interpretation. So we said our reference level was, nice weather. So start with 1,240 pedestrians on a nice, what is the day of the week? The day of the week is, if I do levels as factor, data, all, weekday. This will tell me the base level is the first one there, which is Friday. If is night, multiply by 0.87. And then, you basically do that for all of these other categories. If the weather is bad, multiply by 0.46. If it is raining, by 0.6. If there is precipitation, oh no, this isn't binary. Remember, precipitation is like the number of inches of rainfall. Let's look again. So precipitation is the hourly precipitation in inches. So for each hour, or for each inch of precipitation, or I should say, multiply by something, we round this. This is basically 0 by 0.001 to the power k, or let's just make up a number, n, where n is the number of inches of precipitation. And then if it's Monday, by 0.92, and you just do the same for all of these other factors. And then for the hour GLM, we want to take, for each hour that is past, well, first of all, we have to remember what our GLM was. Our GLM was, where is it? Hour 3, right, which is this. And so this was And so this was the number of hours past 2 p.m., 0.79 to the power of n, where n is the number of hours past 2 p.m. And then temperature nu, and then multiply by 0.001 to the n. N is the temperature, and then these parts with the interaction are a little bit more complicated. So the way to explain this is just to look at the hour GLM variable here and just add an asterisk next to it, and then we'll explain it in the report. So what this says is, we have to first choose this base rate, or the slope. So let's just start with this first, and then we'll make an adjustment for this, this hours variable. So if you have to think about it like this, you actually have 4 different slopes, or 4 different values of your coefficient for this value. This could be, so if it's nice weather, nice night, bad weather, or rain, then the hour JLM is either this or I should say it's this, or it's this plus this, or it's this plus this. Or it's this plus this. So these are the different values. And then when you exponentiate those, you get these. So how would I interpret this? Well, I'll say if it is a nice day, then multiply by 0.79 for each hour past 2 p.m. If it is a nice night, multiply by 0.69 for each hour past 2 p.m. If it is bad weather, multiply by 0.75 for each hour past 2 p.m. If it is raining, by 0.73 for each hour past 2 p.m. This is really the way you interpret the hour variable. So I guess we could make this into a new file. So we're going to do this, and then we're going to take this, and we're just going to replace that, and then add in this, and then copy this. Like that. And this was a lot of work to get this simple table, but it is extremely useful because it gives us a lot of compact information. So this model above gives us invaluable insights into pedestrian activity. So yeah, let's put this again. Let's put this up. The formula below is easy. It will replicate the results of our model within a spreadsheet. You can translate this just by starting at the top row and moving downwards. So this gives us useful insights. This gives us with useful insights as, you know, the most common day to be outside is on Friday. You know, this is the end of the week for many people, and so, you know, people want to get out of the office and spend time outdoors. If it is night, yeah, you know, nighttime is darker. So nighttime, what we should be considering is street lights and illumination should be considered in the new locations. You know, sidewalk, people don't like to walk. Do not walk on dimly lit sidewalks. And so to continue attracting customers during, you know, nighttime hours, we recommend installing, you know, light fixtures around the retail, around the stores. You know, if the weather is bad, you know, weather needs to be considered. You know, maybe when designing buildings in cities that experience bad weather, care should be taken to allow for, you know, for covered entranceways so that people will, you know, come into the store for shelter. This can increase your traffic. Yeah, there's a lot of different things you could say about these, but you could also think about precipitation, you know, day of the week, the day of the week, you know, is going to be the same, you know, regardless of the location. You know, we found we did not see any difference in the weekday during, you know, different, you know, temperature levels. So we recommend launching shopping, marketing campaigns, you know, during the weekends, starting on Friday into Sunday, because the multiples are highest here from 1 on Fridays, 1.34 Saturday, 1.08 on Sunday. Yeah, and then we're down to, you know, the temperature, which we already, and then the interaction between the hour and the effective time, right? You know, time depends on the weather. You know, if it's a nice day, people are in less of a rush and are more willing to stay around outside. During bad weather, as can be seen from the multiple of 0.79 for each hour before or after 2 p.m. If it is bad weather, if it is night. Does this really make sense? This is somewhat confusing because, night is obviously related to the hour. So, if it is nighttime, you already know that it's past 2 p.m. If it is bad weather, so I'll just say that, a word of caution, caution needs to be taken when interpreting the third to last entry, which refers to the night and time relationship. Clearly, when it is night, then it is past, like 2 p.m. already. And so this value of 0.69 needs to be taken with a grain of salt. Let's not say that, that's too informal. It needs to be, should not be, what would not commonly apply. And then I would just sort of, break up this massive wall of words into some more manageable chunks. So like this would be like the introduction, talking about the business problem. And then here we're talking about, the results with 11,000 observations, the number of pedestrians in each hour. Okay, and here's our data background. So we're talking about this data exploration. It's going to be this process. Shopping and spending are related to our emotions. This is honestly a lot of words here. This is basically writing a novel about shopping and retail management. This is probably more than is needed. So I would just go through and maybe delete some of these. Yeah. So I'll just say humans are habitual creatures. The day of the week alone was not sufficient to guarantee. Because I'm already talking about the weather here. So let's just say the time of day is closely related. Okay, and then we already talked about that. We advise against marketing to walk-in customers. This is actually, this advice I think would be better suited down in the modeling section. So I'd say we advise against marketing to walk-in. Looks much better. And then we're talking about the time of day, the different times depending on the time. And then we talk about the different types of models. So this is where we talk about model building. So we have data exploration, model building, and then this would be model validation. Now this is still model building. Actually, let's make this even simpler. Let's just call this predictive modeling. And then, results. So we should talk about how we arrived at this model. How did we measure performance? So we're going to go back up to the section where we do that. So we were looking at the RMSE. So we used a common statistical measure of performance known as the root mean squared error. When this is high, the model is a poor fit, and when it is low, it is a good fit. This is we can be assured that these results will generalize in real life because we used a blind testing methodology known as validation testing. We designed our experiment. We designed an experiment to test to confirm using validation testing. This keeps part of the data in a blind holdout set and only used a holdout set that we never looked at, that our actuaries did not look at until the very end of our report. Once we had chosen our model, we ran these these observations, these records. We ran this data through and verified through our model, verified that the predictions matched the actual pedestrian activity. And then we can say the GLM had the best performance out of the 3 GLMs and 2 decision trees tested. We also considered how easily you would be able to use the result. And as you can see, you will see below, this model below gives us invaluable insights, gives you invaluable insights into pedestrian activity. The formula will replicate the results of our model within a spreadsheet. You can translate this just by starting at the top and moving downwards. Yeah, and then it's always a good idea to say something like next steps or conclusion. So, this result shows that pedestrian activity is not random and is based on the weather, is not random and is based on known and quantifiable conditions which are publicly available. You can use this. So and then try to think of as many limitations or constraints as we can. So we know the data was only from New York. And so in other states with different weather patterns and populations, these results would necessarily be different. A thorough re-updating on new data should be conducted. Also think about, there were only, 7 variables, only a few variables used. And so there is information that is not being included, such as, whether or not there is a COVID pandemic that is enforcing social distancing, or the population of the area. Whether it is a city or a suburban store in more, or whether it is a city or suburban location. And then as a final step, it's good to go back to the, well, at this point, it would be a good idea to upload this document to PROJECT so that you do have a fail-safe. And then with all of your extra time, you can go back and just polish up, the earlier parts of the report, check the spelling, make sure that the graphs are clearly labeled. It might be better to redo these, hand drawings with like straight lines if you wanted to. So you could go to Insert, Shapes, Lines, and then underneath, or add a caption and say, green line shows overall trend. And that sort of creates, there we go. And I do notice that on these reports, on these graphs, they are quite large, take up a lot of the page. So I'm going to make them smaller and then just throw them in the center. I'm going to keep this one big because that's just, and also comment on the base levels. The base level are not important because all days have same number of observations. Alternatively, because the median